Hi guys. I had about one, two, three, four, five, six people come to Sunday tutorials and kind of understanding that you guys who didn't come and are going to get the study guide and then realize that this transformation is not as easy as you thought it's going to be. And before that whole sense of, oh goodness, the test is Thursday or Friday and I don't know how to do this, that sets in. Here's an overview. Yay. Okay, so let's go over the transformation rules. Okay, and I had an investigation on it. I don't know how effective that was, but basically, if you have a function, okay, I'm going to go over all of the rules. So basically, if you have a function such as g of x, and it has been transformed from f of x, and this is the way to write it when you are trying to focus on just a universal way of writing all of the functions, okay? And then you can have specific functions written to show the transformations. Okay, so first of all, you know that C and D are going to be the translations. Okay, those are going to be the translations. So the C tells us right or left, and D tells us up or down. For example, if you had, let's see, g of x, and that was x minus 4 squared plus 2. We know that it moved right 4 and up 2. Okay. And remember, when we did the investigation, if you write it right next to the number that the addend is actually working on, just like that, then you know to take the opposite of both. So that's going to be right 4 and up 2. And that's the y, and that is the x. And those are literally the variables that you are adding or subtracting, or adding negative integers or positive integers too. Okay, or positive or negative numbers. Okay, and then we come to this a and b. Inside of the function, that is going to be a horizontal, because literally it is multiplying the x value. Okay, and then we realize that we have to take the reciprocal. We have to find the reciprocal of whatever that is, and then that becomes the scale factor that we are going to multiply the x to by. Okay, and then the a is going to be the vertical dilation, and we don't have to take the reciprocal. It states the scale factor. Okay, and the scale factor is the determining factor. Like if you actually look at the number that you are multiplying the y or the x by, it's going to give you whether or not it's a stretch or a compression. And that way you didn't have to memorize it. So if you, for example, you had g of x equals 2 f of x, and this is a universal function, you see that the 2 is a vertical stretch. Why is it a vertical stretch? Because you are multiplying the output, and output is a y, and y is naturally in its state up and down. That's a vertical, and it's a stretch because that scale factor is a 2. 2 is bigger. It's going to make it bigger. Okay. And I said another way to write that is to move that 2 to the other side, and it becomes 1/2 g of x, f of x, which tells us, hey, we just need to multiply, you can literally see that you have to take the reciprocal of 1/2 to find that the scale factor is 2. Okay, in that same aspect, if I had a g of x, and this is equal to, for example, f of 1/4 x, notice that that is going to be a horizontal, because literally you are multiplying the x, okay? And an x value is traditionally on the graph a left and right value, okay? And so that is a horizontal. Now you have to take the reciprocal to find the scale factor, which you actually multiply the x value by, which is 4. Okay, so when you multiply by a 4, it tells us that it is going to be a stretch. And you multiply the 4 by, so it'll be x, whatever the inputs were, and you multiply it by 4. Okay? And then if it's a negative, if a is a negative, this a value is a negative, notice what is going to happen is that you are going to multiply the y's, the outputs, by a -1. So for example, let's go ahead and make that a g of x. That's not a good color. Let's pick another color right here. If you make like g of x equals a negative f of x, okay, I could still move this to this side. -1 times a g of x. What are you doing? You are multiplying. Multiply the y by a -1, which becomes a reflection over the x-axis. If you had, let's say a g of x equals f of -x, you are literally multiplying the x by a -1, so that becomes a reflection over the y-axis. So one of the things that you need to know is, number one, the description. The description of what is happening. Okay, was it a vertical stretch, compression? And then you have to know what you exactly have to do, either to the input or the output. Okay, the actual, what would be the mathematical result. If you know both of these, then you're going to be good. Okay, so let's look at some of the examples. These I did in your class. Okay, it says identify the parent function. Okay, we identified that it is an absolute value. We describe the sequence of transformations, then sketch the graph. Okay, so this is informing you of how to sequence the transformations so that you have the proper graph. Because if you add 6 to this, to the x, and then you multiply, that's going to be a different number than if you multiply by, it's not even a 3, multiply by the reciprocal of 3, which is 1/3, and then add 6 to it. It's going to be a completely different thing. Okay, so the very first thing you do with this is, let's go ahead and rewrite it, because up here you notice that this b has been factored out. Okay, let's go ahead and rewrite this as, I'm going to factor out the 3, and that becomes x minus 2. Okay, now the parent function of this is an absolute value function. So I'm going to go ahead and draw my table. 0, 0, and it's going to be 1, 1, negative 1, and 1. I can keep on going. 2, 2, negative 2, 2. Okay. The two things that happen, okay, from the original function to transform this into f of x is that we have to go right. We have to go right 2. And with right 2, that means that we add 2 to the x. That's one of the things. This 3 tells us we have to take the reciprocal. We're going to multiply 1/3 multiplied to the x. Okay? But we have to know the sequence. Now, if I factor it out like this, it's going to tell us, if I follow the rules of PEMDAS, it's going to tell us to go right 2 first and then multiply it. But I have to look at the original function. The original function tells us to first multiply it, okay, by that 3, and then we subtract 6. So that'll tell us the sequence right there. So number 1, we're going to take the x's and we're going to multiply it by 1/3, and then we're going to go right 2 on it. Okay, so that gives us a sequence of what to do. The original function is going to do that. Okay, let's go ahead and do that. And notice that, well, this is a horizontal. The description of this would be horizontal compression. And I'm looking at this scale factor to tell me that 1/3 is going to make those numbers smaller. Okay, and this would technically be a translation of right 2. Okay, technically. Okay, so once I do that, I can take my points. Okay, and this is the outcome whenever you multiplied. Okay, multiply. Let's use a different color. This is a multiply by 1/3. So that's going to be 0, 0. And then 1/3, 1. Negative 1/3, 1. And that's going to be, it's not going to show. 2, 2/3. Yeah, definitely not going to show. 2/3 and 1. Oh, 2. I'm sorry. And negative 2/3 and 2. Okay, so I can go ahead and graph. Oh, no, I can't. I forgot to do number 2 right here. So after you do that, you're going to take this, and with the x points, you're going to now add 2. Positive 2. So we have 2, 0, 2 and 1/3, 1. Notice that the y values do not change at all. And that's 2 minus 1/3. So it's going to be 1 and 2/3, 1. And then we have a 2 plus 2 and 2/3, 2. And then we have a 2 minus 2/3. So that is going to be 1 and 1/3, 2. Okay, when I plot those points, we have a 2, 0, and a 2 and 1/3, 1/3, 2 and 1/3, 1. 2 and 1/3, 1. Yeah, I don't want to use those points because they're kind of like gonna make my graph kind of funky. So 2 and 1/3, 2, but I just have to, so that's 3. So that's 2.5. So 2 and 1/3, 1. Somewhere there. Okay, and then let's see, 1 and 2/3 right here. somewhere there. Okay, and then 2 2/3. 2 2/3, 2, somewhere there. Okay, a little bit closer. Right there. And then 1 1/3, 2, somewhere right there. Another good point to actually put in to start off with is maybe like 3 and 3, because you know that that's divisible by 1/3, or it's divisible by 3 when you divide it. Okay, so that would actually transform that into, let's see, it's going to be 1 and 3 and -1 and 3. And when I add 2 to that, that's going to be 2 and 3. And then 3, 3, 3, and 1, 1, 3. So 3, 3, and 1 and 3. There we go. Now if you look at the parent function, 0, 1 and 1, and 2 and 2, 2 and 2, and -2 and 2. That right there is the parent function. So you can clearly see that that point now move right to, and it's definitely looks like we vertically stretched that. Or we can say we horizontally compressed it in. Okay? Okay. Next problem. It says identify the parent function, describe the sequence of transformation, and then sketch the graph. Okay, so the parent function, we definitely know it's a square root function. Okay, let's go ahead and rewrite it. And why do we need to rewrite it? Because that right movement or left movement, that horizontal translation is going to change based on how you rewrite it. I don't like that pen, it's too thick. F of x equals 3 square root negative x, factor out that -1, minus 4 minus 2. So a couple things that we know with the translation, we know that it's a right 4. It's a right 4. And how does that actually mathematically translate? We have to add 4 to the x value. Okay, we know that based on here that it is going to be a down 2. So how does that translate? We're going to subtract 2 from the y value. Okay, and then we take a look at the negative right here. That negative is a reflection over the y-axis, which mathematically we take -1 and we multiply it to the x, or the input. Okay, and then we take a look at this 3 right here. Okay, that 3 is going to tell us that that is a vertical stretch. Mathematically, that's going to tell us that we have to take the y value, 3, and multiply the y values. Okay, square root function, I'm only going to use a couple points. The parent function, we started off with 0, 0, and we can do 1, 1, and then we can do 4 and 2. Okay, now let's look at the sequence. In what order do we do this in? Let's look at the original function right here. Okay, let's take a look at this original function. What happened to it? First, the input got multiplied by -1. Okay, that's the reflection. That's the first thing we do. And then the x, you add 4 to it, which is the right 2. It's 2. And then you take that whole thing, and then you square root it, of course, but then you multiply it by a 3. So that's going to be the vertical stretch. And then you take that, and then you subtract 2 to it. Okay, so that's going to be the sequence. Okay, so based on that, let's do the first one, x and y. I'm going to reflect over the y, -1 multiplied by x1. So I'm going to multiply these by -1. So 0, -1, -4. Y is going to stay the same. Now, the next thing that we're going to do is take right 4. So that's a +4 on whatever you changed. So 4, 0, and then 4 is going to be 3, 1, and then that's going to be 0, 2. Okay, now it's a vertical stretch, so you multiply the y's. So you're going to multiply the y's by a 3, so 4, 0, 3, 3, and 0, and then you multiply 2 by, there you go. Now, the last thing we do is take the y values, and it tells you to subtract 2. We're going to subtract 2. So x values are taken care of, and the y values, that's -2. And that is a 1, and that is a 4. I'm just going to graph those points. We had a 4, -2, and a 3, and 1, and 0, and 4. Just like that. Connect those. Try to do it as best as you can. Just like that. Okay, if I draw the parent function, 0, 0, 1, 1, and 4, 2, there's the parent function. You can clearly see that it reflected over the y-axis, okay, and then it went right 4, I'm sorry, okay, we went right 4 to here, and then there was a vertical stretch. It looks like definitely this function stretched out vertically, okay, to become that function right there, okay. And then we had to go down 2, okay? So we had to go down 2. If I can actually draw all of that, it's going to look like reflected. So that's 1, 1. And you can actually go through these points, these tables that you made, and you can see the transformations. -4 and 2. So it reflected like that, and then it went to the right 4, so it started here and all of the points moved right 4 that way, and I don't want to mess up this graph. And then each of the y values increased by a scale factor of 4. That's why you see this stretch in the pink graph, okay. And then it moved down 2. Okay, and that's what you want. These little tables right here, these little transition tables, are going to help you out so much. Okay, good job. Now, I threw this one in here, even though it's easy, because maybe you haven't seen a transformation of a rational function. Okay, so that's why I threw one of these in here. So the parent function is a reciprocal function, okay, which looks like that. And if you see that and see what changes happen to it, we saw that there was a +4, and we treat it just like a number being added into the function, okay, inside the function. So, and it affects the x. So that would be a horizontal translation, or it's actually going to go left 4. Okay, and over here, that is outside of the function, so it's just going to go down 3. Okay, so if I use my x and y values, and if I take a look, and I can use this table, I'm going to actually include asymptotes too. Okay, so if I have a 0, if I put a 0 in here, that is going to be undefined. That's going to be my vertical asymptote. Okay, and if I had a 0 here, this is going to be undefined. And then if I put a 1 in here, that's just going to be a 1, and a -1, that's going to be a -1. And that's enough points. Okay, now what does left 4 mean? I'm going to subtract this by 4. Let's use a different color. I'm going to subtract this by 4, and we're going to subtract this by 3. And what you're going to end up with, and you can do it on the asymptotes too. So your asymptote is now going to become -4, undefined. And then this is, I don't know what this is going to be, but that changed the y value. And still at -3, that's going to be undefined. And then that is going to be a -3 and a -2. And that is going to be a -5 and a -4. Okay, so at x equals -4, right here, there is my vertical asymptote now. And you can see that. You can set that denominator equal to 0. Okay, and then my horizontal asymptote now becomes -3 right here. And you can't really see that. And some of you guys were saying, hey, look, there's a 1, so it shouldn't the horizontal asymptote be a 0? But then if you actually solve this or simplify this, f of x equals 1 over x plus 4, there is this -3. So if I make this a common denominator of x plus 4, it's going to be 1 and then -3x plus 4. And this is going to be a 1 minus 3x and a -12 over x plus 4, which tells us it's -3x and a -11 over x plus 4. And you notice the constant, if I put a 1 there, the horizontal asymptote is a -3, which my chart told me that. Okay, and then the points within the two quadrants that you're going to get is going to be a -3 and a -2 right here, and a -5 and a -4 right here. So here lives my function right here. Just like that. And I can compare it to the parent function. I can make this graph look really messy. Okay. The vertical asymptote moved left 4. And then my horizontal asymptote moved down 3. And this 1, 1 right here. And this negative 1, 1. Okay, move to be these points right here. Okay. Good job. Okay, and the sequence of this, it doesn't matter because the left 4 affects the x and the down 3 affects the y. You do them together. Okay, number 5. Describe the series of transformations of g of x and then write the equation of g of x. So this is a quadratic. Okay, and one of the things that we were trying to illustrate when we were doing the investigation was that if we had g of x equals like inside of the function, if it was f of 2x, and that's a horizontal compression. Depending on the function, okay, that horizontal compression, because this is a scale factor of 1/2, you're multiplying, and you're multiplying the x's by it, and that's a horizontal compression, but because of the fact that this is written as universal function form, and I told you guys that a horizontal compression is actually, you can actually define this as a vertical stretch if you take it outside of the function. But this function doesn't define what the actual function is. This is just a universal way of writing this function. Okay, so it is very important that you understand that depending on what the function is, the vertical stretch scale factor is going to change. If it was g of x equals the 2x to the second, now that scale factor of 1/2 in a horizontal compression, if I take it out, becomes a 4 scale factor of a vertical stretch. If it was a absolute value function, okay, that 1/2 horizontal compression, now if I take it outside of the function, becomes a 2 scale factor of a vertical stretch. Okay, because if you just take the 2 out of the absolute value, if it was g of x equals a cubic, like that 1/2 horizontal compression scale factor now becomes an 8 scale factor of the vertical compression. I'm not compression, but stretch. Okay, so when you write something as a universal function just like this, it's not clearly defined. Yes, the horizontal compression is going to be a vertical stretch, but we don't know exactly what the scale factor is going to be because the function was not defined. Okay, so I want you to be aware of that. If you're just going to transition to vertical stretches and vertical compressions, and if I ask you the scale factor, you're not going to know if it's written this way. Okay, now going back to this, okay, let me go ahead and erase that. Let me just make a large eraser. You can clearly see this is a quadratic. You can clearly see this is a quadratic function. And then, so one of the things that happened was that it reflected over the x-axis. It was a reflection over the x-axis, which tells us mathematically that means we take the y values, y multiply by -1. Okay, and then so this is a little trick. I think some of you guys caught on to it whenever we were graphing functions. and I was asking you to graph whatever, any kind of function. That little first point from the vertex tells you the dilation. So for the parent function, notice that I go up 1 and to the right 1, or up 1 to the left 1. Okay, so up 1 and to the right 1. And then up 1 and to the left 1. Okay, that's a slope of a plus or minus 1. And since this is a quadratic, it's going to produce both the plus slope and the minus slope. Okay, if I look in that same regard to this vertex, and I look at that first point, okay, down 1 and to the right 1, or down 1 and to the left 1. We know it reflected over the x-axis, so it's going to be a down movement. Okay, but if you notice that the scale factor did not change at all, it's all 1s. So there's not going to be a dilation. Okay, and I can do the same. I went up 1, 2, 3, 4, and to the right 1, 2 to get to this next point, and I went down 1, 2, 3, 4, and to the right to get to this next point. There is not going to be a multiplier at all. It's not, because the points ended up in the same position from the vertex. Okay, so there's no dilations here, and I could clearly write that, no dilation. Now let's go ahead and see what other movements we had. Okay, so we know that it went 1, 2, 3, 4. So 4 to the left. 4 to the left would mean mathematically, it would be a -4 on the x. Now let's go ahead and create our g of x. G of x, and I could write this as a universal function, f of x, and let's identify it, multiplied by a -1. So g of x equals negative f of x. And then move left, g of x equals negative f of x plus 4. Or if you wanted to write it as a quadratic, here's our parent function multiplied by negative, and then moved left 4. Like that. Either one will work. Okay? Good job, guys. Okay, describe the series of transformations. Notice that it doesn't say sequence because they don't have to be in order. Okay? Of g of x, for g of x, and then write the equation. Once again, it's a quadratic. Okay, I can write it both ways. G of x is we're going to transform f of x in some way. And then, or you can write it as g of x equals x squared. So let's see what happened to it. Okay, I'm going to take that vertex. Okay, first, we can see that vertex 1, 2, 3. Okay, that was a right 3, which tells us mathematically that we have to take plus 3 with the input, with the x. And then it went 1, 2, up 2, and that is a plus 2 with the y value. There was no reflections. Okay, now you can tell that this graph from the parent function, from the parent function from the parent function, you can tell that you can say that we could squished it this way. It could be a vertical compression, which would mean that you would have a scale factor of greater than 1, okay, and that would be outside of the function. Or we could say that it is a horizontal stretch, okay, which would mean that the scale factor would be between 0 and 1, and that would be inside of the factor. When you have a choice, I always choose vertical compression, because vertical compression doesn't mess with a lot of things inside the function. And so I'm going to choose that. I'm going to try to do the vertical compression. Okay. So I know it's a vertical compression. And so we have to find the scale factor. We have to find the scale factor, and the scale factor multiplies the y value. So I put a point there because those points are important. Okay, we have a 1, 1, up 1, and to the right 1. Okay, and then I think I did a... So if you take a look at that point, okay, and if you went up 1 and to the right 1, we didn't go up quite as 1. That looks like a half. 1/2 and right 1. So that tells us that if I actually make a table, then you can see the table. Okay, it's going to be 1, 1, and it transitions to x and y, which will be and I'm just making a table from the movement of the vertex. And this is a very good way for you to see. Okay. And then the next one, to get to this next point right here, we go up 1, 2, 3, 4. 1, 2, 3, 4. We went up 4. Oh, wait a second. I'm putting it on all different kinds of graphs. Okay. So x and y. So if you went up 1 and to the right 1, this would be up 1/2 and to the 1. The next one would be up 4, okay, and to the right 2. And maybe to get to this point right here, you would have to go up 1, 2, and to the right 2. If you look at that, and remember, the scale factor is a number that you multiplied the y's by. So how did this 1/2 become this 1 become 1/2? You multiplied it by 1/2. How did this 4 become 2? Well, you multiplied it by 1/2. And just like Samir realized, and this is perfect. He realized this on his own. Okay, that you could just take the movement from the vertex. Okay. Wherever the vertex may have translated to, and look at those points and just write it out maybe on a table, then you can clearly see that this got created with a scale factor of 1/2. Okay, so it is a vertical compression with a scale factor of 1/2. Now, after you do that, you can go ahead and write your equation. So g of x got created by 1/2. That's where the vertical compression goes. X, right 2 is going to be a -3. Oh, whoops. I'm writing this as a whole function, universal function notation. So x, and then -3, and then +2. Or if I just write it as a quadratic, it would be 1/2 x minus 3 squared plus 2. Remember, for a universal, you have to include that square. Okay? Good job, guys. So I'm going to do some problems from the review. Okay?